Okay, in the previous class, we have seen uh, the transistor construction, how the transistor will be constructed, what are the parameters we have to keep in our mind in order to construct a transistor. Okay, so that means what is the theory behind why different type of materials we had to use. Okay, so why we have to use the gate oxide, why we have to use the metal on top of it, why we have to use the source and drain, all the information that we have seen in the previous class. Okay, so let us revise again the same concept in a different manner. Okay, so just understanding of the MOS FET operation by applying some additional inputs. Okay, so before going to that one, exclusive for the MOS transistor, that an N-type transistor. Transistors generally broadly classified into two types. One is bipolar junction transistor. Next one is field effect transistor. So since the bipolar junction transistor has got a high power consumption, so we focus on field effect transistors. Here also we can see junction field effect transistor, JFET. Another one is MOS FET. So the right hand side you can see metal oxide semiconductor FET. It is also called as MOS FET. Okay, just a second. So here is called a MOS FET, metal oxide semiconductor field effect transistor. This is JFET. Okay, junction field effect transistor. So the primary deviation from junction field effect transistor to the MOS field effect transistor is that here also the field effect concept is involved in this one. But power consumed by this junction field effect transistor is very high. So high power consumption. Okay, power consumption. So people, we don't want to use this one. So obvious solution is we have to go for MOSFETs. MOSFETs also classified into two types. One is enhancement mode type of transistor, and the next one is depletion type mode transistor. Okay, this classification is based on whether the channel is present, whether the channel is present or not. Channel is present during the fabrication. So very important, during the fabrication. So what do you mean by the fabrication? We will see later on. So whether the channel is present during the fabrication or not, depending upon that, MOSFET can be classified into either enhancement mode or depletion mode. Okay. So it is also having two flavors. One is called N-channel MOSFET. For example, channel is N-type material. If the channel or immersion layer is N-type, then it is called N-channel MOSFET, or simply NMOS we can call it as. So if it is a channel is a P-type, we normally call it as P MOSFET, we can call it as, right? Similarly, the channel is already present while we are fabricating the transistor. If it is a N-type channel, it is called NMOS depletion mode type of transistor, depletion, and a PMOS depletion mode type of transistor. Okay, so it is a NMOS enhancement mode, PMOS enhancement mode. So unless otherwise we state that a particular transistor is a depletion type mode transistor, we cannot say directly it is a depletion type mode transistor. Okay, default we normally use enhancement mode type of transistors because the power consumed by the enhancement transistor is less compared to the depletion type mode transistor. Because once the channel is present, we have to deplete the channel. That's the reason why we can use the MOS transistor. So something is already present. If you want to eliminate something, the initially starting from the starting point onwards, the power is consumed. So we don't want that kind of devices. When and where exactly specific places are there, there only we have to use the depletion mode type of transistor, right? Fine. Next. So in the last class we have seen that this is the construction of the MOS transistor. Okay, it's a three-dimensional view. It has got a source. This is called source. So this is a source region. This is called the drain region. So why the source and drain are induced in why it is necessary to provide all these things that we have seen in the last class. Okay. So and we have here very important one is gate oxide. It is a gate oxide is white color hash lines are there. No, that is called gate oxide. On top of it is a metal. It is a metal conducting plate. So therefore, this is the metal oxide semiconductor MOS. What is the transistor operation? Field effect transistor operation will be there. Okay, and we need to provide an external for the external communication purpose. We have to use the metals here. This is the one metal. This is also one metal. This is for external connection. Okay, this is a source. It's a drain. It's a generally it is a metal we are using. Previously, people were used polysilicon. Okay, the polysilicon sheet resistance is very less. So that's the reason why people were used this kind of thing. Okay, so sorry, I'm extremely sorry. The melting point of the polysilicon is high compared to the metal. Previously, people were a problem with the metal is one of the gate for the transistor. Later, they have realized with the metal by using the polysilicon, because the melting point of the metal is very less. So while we are fabricating a transistor, gate will be not able to realize. So therefore, people use the polysilicon because its melting point is very high. But it is also facing some kind of problems while we are going for the smaller and smaller technologies. Okay, for example, 65 nanometer, 45 nanometer. So from 45 nanometer onwards, this is a problem is arises. So that's the reason why again the people come back to the metal gate normally use. So a very important thing is that MOS FET is actually considered with the two types. One is whether it is a metal gate technology we are using, or polysilicon gate technology. Polysilicon gate technology we have to use. So generally, initial days they were used this one. So they found the problem with this one. They went for this one. Again, there is a problem with this one, and come back to again the metal gate technology only, right? So now, how do we use the physical layers to construct this one? We will see later on. Okay. So what I have done first of all, the construction, the construction concept, the theory of construction of MOSFETs. MOSFET. That's what we have seen previously. So today we are going to look at the MOSFET operation. The MOSFET operation. Qualitatively is very important. Qualitatively we look at this one. The third one is by using physical layers. The construction of MOSFET can be seen. Okay. So first మనం ఇది చదివాం, మనం ఈ థియరీ ఏంటో చదివాం. నెక్స్ట్ ఈరోజు క్వాలిటేటివ్గా దాని ఆపరేషన్ ఏంటో చదువుతాం. నెక్స్ట్ క్లాస్లో by using the physical layers, how do we construct the structure? Okay, fine. Okay, as I mentioned that the MOSFET is can be operated in two ways. One is called enhancement mode, another one is called depletion mode. Okay, so why it is called enhancement mode? Because so we enhance the channel for the current. Okay, so if you want to have a more and more amount of the current is required, we have to enhance the channel. Okay, for example, we consider this the MOS transistor, the gate polysilicon. So we have a source, we have a drain. For example, this much channel is there. Okay, small amount of the current will be produced. Okay, For example, if this much amount of the channel is there, this much channel is there, then some more current will be produced. Okay. For example, if you consider that this much amount of the channel is there, more amount of the current will be produced. That means we have to enhance the channel for more current. Okay. ఎప్పుడైతే ఛానల్లో ఎక్కువ క్యారియర్స్ ఉంటాయో మోర్ అమౌంట్ ఆఫ్ ద కరెంట్ అనేది పాసిబిలిటీ ఉంది. దట్స్ వాట్ ద ఫండమెంటల్ థింగ్ యూ హ్యావ్ టు రిమెంబర్. And in case of depletion mode, we have to deplete the channel for the current. Okay. So initially what happened here is that I will show you after one minute. Okay. So this is the source, this is the gate, this is a polysilicon source drain. Initially there will be a channel. Initially there will be a channel, something like this. Okay. So what we have to do, we have to deplete the carriers from the channel. So initially this is what, now it becomes this much value. So now this becomes this much value. Okay. So it is not there. So what we have done, we have deplete the carriers from the channel. Okay. So therefore the current is initially large amount of the current is there. While depleting the carriers, less amount of the current can be seen in the depletion type mode transistor. That's what you have to keep in your mind. Okay. So therefore enhancement mode type of transistor means for the current purpose we are using the enhancing the channel. In the depletion mode type of transistors, we have to deplete the carriers for the current. I hope you can understand the enhancement mode and depletion mode. Okay, let us see some more detail about this one. Okay. Okay. So this is what the two-dimensional view of the transistor. As we have seen, for example, look at this diagram. It's a three-dimensional view. It's very difficult to draw the diagram something like this, right? It is very difficult to draw all these things and three-dimensional way something like this. Instead, I'll consider only this part. I'll consider only this part and necessary information on this one. Therefore, this is called side view. Okay. Okay, the side view we have to consider. So let us see the side view. Okay, this is what the p-type substrate or p-type bulk here we have. So we have a source, we have a polysilicon, sorry, we have a gate oxide. We have a gate oxide here. On top of it, we have a metal there. On top of it, we have a metal. So normally they, in this particular textbook, they use it for the polysilicon gate technology. Polysilicon gate. Okay. Under this polysilicon gate, this could be the polysilicon. This is polysilicon. So on top of it, we have a metal. So we have a metal for contact. This is the metal for contact. This is also metal for contact. Okay. So this is the source. This is the drain. So why this is the spaces they have introduced here? What this space belongs to? Okay. This is actually a depletion mode type of depletion charge or space charge, we can call it as. So normally, for example, we have a p type of substrate here, p. Whenever you are diffusing something inside of this one, edges of this particular diffusion, the whole electron recombination will be takes place. That's the reason why near the boundaries, the space charge region will be developed. Okay. Usually, sometimes we ignore that one, but it is there. Okay. So therefore, this vacant place we can call it as a depletion charge, or what we can call it as space charge region. Okay. So therefore, this is called enhancement mode type of transistor because there is no channel here. If you observe carefully, there is no channel at all. Okay. Here there is no channel, right? So ఇక్కడ మనకి ఛానల్ లేదు. So if you channel లేదు, channel ఎప్పుడు వస్తుంది మనకి when the channel will come into the picture by applying the potential difference between the gate and substrate. Okay. So in generally we have to apply the gate and substrate, then only the carriers will be induced here. Okay. So but one more thing is that if you want to transport a carrier from source to drain, we have to apply the potential difference between these two also. Antena? So therefore what I can say is that, see, please remember very carefully one point. I'll tell you one point, very interesting point here. Okay. The potentials that we already defined that one. Okay. So what is that? So if you want to have a negative charge here, because minority charges are required, right? That's concept we have studied earlier. We have to apply the positive charge here. Okay. With respect to the substrate. Now, if you want to transport a carrier from source to drain throughout this channel, along this channel, we have to apply potential difference here. What the potential that should apply? Negative potential I should apply. Positive potential I should apply at this place. Then only the carriers can move from, then only the electrons move towards the positive side, right? So therefore you can see, observe, this is the negative sign. This is also negative sign. Therefore, we are tempted to connect these two things, something like this. So knowingly, unknowingly, these two are at the same potential. We have connected like this, but actual truth is that, so we have to connect it obviously. Otherwise, body effect will arise. Body effect will arise. Okay, what do you mean by the body effect of the transistor? Okay, so the body effect of the transistor is nothing but, whenever you are constructing one particular transistor, its threshold voltage is fixed. Okay, that means the voltage at which inversion charge is induced is fixed one. Okay, but whenever the source and substrate are at different potentials, okay, the threshold voltage will vary. The threshold voltage of a transistor will be varied. That is not advisable one. So therefore that is called body effect. What is the body effect here is that, whenever the source and substrates are at the different potentials, the threshold voltage of a transistor will be varied. This is known as body effect. So the body effect should not be entertained at any cost. So therefore, so one way is that because these two are at the same both are at the negative potential, that's the reason why we connected this one. But the actual truth is that, in order to avoid the body effect, we have to connect the source and substrate at the same potential. Okay, now fine. So far so good. So I can say that now, instead of saying that gate to substrate potential to provide the inversion charge, I can say that gate to source. Okay, gate to source, I can consider that now. So VGS now we can call it as, instead of substrate. Okay, VGS is transfer V gate to V substrate. The potential at the gate to the potential at the substrate. Not so, I'm extremely sorry. It's not a substrate, it is source. It is a source, right? Are you agree with me? Fine. So therefore, we have to apply a sufficient gate to source voltage, then only the channel will be formed. That's why it is called enhancement mode type of transistor. But whereas a depletion type mode transistor, the channel we have to create while we are fabricating the transistor. So that's what important. While we are fabricating the transistor, we have to create the channel. As soon as we are creating the source and drain, we have to create these two things also, channel also. So therefore, implanted channel, that is called. It is called implanted channel. Okay. So therefore, if you want to make use of this transistor, we have to deplete this charge. Implanted charge must be depleted. Okay. Then only it is possible to use for our applications. Right. So therefore, since the depletion mode type of transistor consumes a lot of power, we use enhancement type of mode type of transistor. Right? Fine. Fine. Now let us see the operation of the transistor. Construction, we have recapitulated what are the different modes of things are there. Now let us see the MOS FET operation. So the MOS FET can be operated. So let us consider depletion type mode type, sorry, enhancement mode, that to N-type channel. Okay. So here we have an oxide. On top of it, we have a polysilicon. So this is the body. We have a source. We have a source. We have a drain. N plus, N plus. So we have to use the metal lines over there. So this is the one metal line. This is one metal line. This is also one metal line. So therefore, this is called, what we normally call, this is NMOS transistor, NMOS FET or NMOS transistor. So it has got a p-type substrate, right? Don't forget about this one, p-type substrate. It's a p-type substrate is there. For the p-type source and drain must be n-type. So normally this is called gate, this is called source, this is called drain. So this MOS transistor, this NMOS transistor can be operated in three modes. One is called cutoff region, three region of operations: cutoff region, linear region, saturation region. So this is a symbolic representation of enhancement mode type of transistor. It is what the behavior of the transistor by applying the different potentials. Okay. So let us understand this concept, some more detailed discussion. Okay. So that means that there is a two possibilities are there. As everybody knows that there are the two possibilities are there. We have to apply the potential between these two. Okay. So already we have seen it's a minus, it is plus. Okay. And therefore the charge will be developed here. If this Vgs value is less than the threshold voltage of transistor, the transistor becomes off. The NMOS becomes off. So therefore, for example, you consider this one. Consider this one. So this is the line that is going from origin to this one. So what this line says that VDS, VGS is less than threshold voltage of the particular transistor. When VGS is less than VTH of a transistor, there is no channel is formed. If there is no channel, there is no point of transportation of the carrier from source to drain. If there is no channel, there is no possibility of the transportation of the carriers from source to drain. Right? So therefore, the current value is equal to 0. Even if you are applying the VDS value, whatever the value you apply, it doesn't work. Let us consider this is the second point. So VGS, okay, if the VGS value is greater than threshold voltage of a transistor, that value is equal to, for example, VG1, for example. Okay, that means that yes, I am saying that. Yes, I am saying that. Yes, I am applying the potential, that is VGS is greater than VTH. Therefore, the channel is formed over there. Now I am applying the potential difference between the source and drain, minus and plus. Therefore, obviously the carriers can move from source to drain. Obviously, the carriers can move from source to drain. Right. So therefore, what I can observe that, So the first line is connected to the 0. There is no doubt at all. Okay. The second line, if you consider, it is go on, go on, go and go on, and it reaches to some steady point. A small value of the VGS we applied. Suppose yes, VGS is greater than VTH. How much? Let us consider. So VGS is equal to, for example, VG1, for example, which means that VG1 is more than that of the threshold voltage of a transistor. That is the case, channel is some fixed channel is present there. If that is the case, when we are applying the VDS value, okay, I'm saying that, for example, you consider this. Please remember carefully. So what I'm saying that when VGS value is equal to, so for example, this one, when VGS is equal to VG1, for example, forget about these things, okay, forget about these points. When VGS1 is equal to VGS1, which means that which is greater than that of the threshold voltage of a transistor. Now what I'm going to do here is that I want to change the VDS value from 0 to some fixed value. For example, VDD and so therefore VDS value changing from 0 to VDD. So this is what the curve is observing. Still, I don't find any kind of visuality while changing the VDS value from 0 to VDD. Now I am going to change another one that is called VGS value, which is greater than that of VGS2, which is greater than that of the threshold voltage of a transistor. That too, that value is equal to VG2, for example. You can see the observe carefully here. It is going something linear fashion, and then it is come back to the steady state. Similarly, if I am applying another gate voltage, the channel will be enhanced. It is more than that of the threshold voltage, but VGS value is greater than that of VGS2, for example. Okay, so therefore you can see, observe, some linear relationship is existed here. After that, it is going back to the saturation level. Okay, so whenever, please listen carefully, whenever the output waveform or the output current is linear relationship with VDS, when IDS is linear relationship linear with VDS for certain values of the VDS, for certain values of the VDS, okay, certain values of the VDS, IDS is a linear relationship with the VDS. There is a linear relationship that existed between IDS and VDS. Clear? So this is called linear mode of operation. This is called linear mode of operation. For example, if the drain to source voltage, for example, the gate potential is not sufficient, that means it's less than that of the threshold voltage, what will happen? Even if you apply the VDS is how much value it is, the carrier is not able to move from source to drain. Right? That means there is no current in that device. That is called cutoff region. That is called cutoff region. In this cutoff region, IDS value is equal to 0. In linear region, IDS value is a linear relation with the VDS value. That's what you have to remember. It's a linear function. Similarly, so certain point of this one, for example, if you draw a line like this, certain points from here onwards, it is a constant. From here on, it is a constant. From here on, it is a constant. But it is here, it's a constant. Okay, therefore, even though if you are changing the VDS value, we cannot find that much change of IDS value that we can see. This is called saturation point. So this is called saturation region of operation of a MOS transistor. So here IDS is, since IDS is independent is not a function of VDS, but actually later point of time it is a function of that one. For the primary or first case understanding, IDS value is not linearly related with IDS is not a function of VDS if it reaches to a certain point of VDS value, right? So therefore, these are the different mode of operations that we can see in MOS transistors. Cutoff region, linear region, saturation region. In the cutoff region, IDS value is equal to 0 because there is no uh, charge is induced under the silicon dioxide. The second one is so we are maintaining the threshold voltage sufficiently, and now we are changing the VDS value, and I can observe the IDS value, and I found that there is a linear relationship is existed between IDS versus of VDS. Okay, fine. The third point, very important, is that even we are increasing the VDS value, okay, so IDS does not depending upon the variations of the VDS. So in that situation, we can call it as saturation region of operation. Right? Fine. So that is what I have defined everything in this point, but very important to note here is for examination point of view, enhancement mode type of transistors are normally off transistors. Since no channel, initially there is no channel, therefore it is normally off transistor. When it becomes on, we have to apply a sufficient voltage at the gate. What is that sufficient voltage? We normally call it as a threshold voltage. Okay. So for the threshold voltage, for an enhancement type mode transistor, for n-channel enhancement type mode transistor, this value is equal to positive. So the positive potential that we have to apply on top of the polysilicon, then minority carriers will be attracted towards here. Similarly, when you are applying the NMOS type depletion mode type of transistor, VTH must be negative. Okay. So for the depletion type, N type MOSFET only, but depletion mode అయితే ఏమవుతుంది నెగటివ్ వస్తుంది. Please remember this point. Okay, so here the relationship between the VDS and IGS, as I mentioned previously, here IDS is a linear function of VDS value. That means something like this. So a linear relationship is existed. So or maybe this linear, or this linear, or this linear. What is these curves saying that? For different values of VGS value. For different values of VGS. Okay. So the cutoff region means the transistor should be off. Okay. So when the channel is not present, we can say that the transistor is off, which means that the transistor is in cutoff region. The transistor is in cutoff region. Okay. Next, the transistor becomes so. What we can say that. The transistor becomes on means there is a relationship must be existed between the VDS and IDS value. So what is the conclusion we can draw here is that very important. When VGS value is less than the threshold voltage of a transistor, the transistor is said to be off transistor. So for the off transistor, IDS value is equal to 0. So which is say that cutoff region. Okay. So when the VGS value is greater than threshold voltage of a transistor, for example, greater than or equal to the threshold voltage of a transistor, here IDS value is not equal to 0. Why? Because some finite value is there. For example, if it is a finite, the linear or maybe saturation means some finite value is there. No, from here to here there is some finite value is there. So therefore, the IDS value is not equal to 0. So if IDS value is not 0, what is happening here? So therefore, one thing is that IDS is linearly varying with VDS. IDS is constant for other values of the VDS. That's what we can observe. Okay, linear relationship means what? So when it is observed, so linear relationship means the channel is formed something like this. So by applying the potential difference between the source and drain, the linear relationship is existed here, something like this. So it reaches to certain point until below the value of the Vgs minus of Vth. Below the value of Vgs minus of Vth, this relationship is holds good. Right? So therefore, when VDS value is less than VGS minus of VTH, linear relationship is existed here. Linear relationship means whatever the value of the VDS that we apply, that will be reflected as an IDS value for a MOS transistor. Okay. So very important thing is that uniform potential is existed along the channel. It's a very, very important one. So the potential that is existed in this particular channel is, as you can see here. So you see here, so the potential that is existed at this in this particular channel is uniform. Ideally speaking, it's not uniform, ideally speaking. Okay. So whereas in case of saturation region, so this is what happening actually. It is come back to this particular one. It's more clearly we can see here. So in the saturation point, linear, so up to this point, this value is equal to available here only. The channel is present up to this point only. Near the drain side, it's not, there is no channel at all actually. So when this is happened, when VDS value is greater than or equal to VGS minus of VTH, this kind of phenomena is observed. This is called as pinch off mechanism. Pinch off, we can call it as pinch off. The channel is pinched off near the drain. Why it is so? When we are applying the positive potential, it becomes a reverse bias. Initially, this is what the depletion space charge region is there. When more and more positive, if you apply near the drain side, near the drain side, this much value is observed there. This one. So even though there is no channel is inverted near the drain, the carrier at the near the drain will be accelerated towards the drain side by the drift of electrons. So therefore, the electrons are taking the drift mechanism. They can travel towards the drain side. Thereby, even if you are increasing the VDS value, the current cannot change. It's a maintain the fixed value. So therefore, this is called pinch off, or the transistor is said to be in linear saturation mode of operation. But anyway, one important point we have to remember is that the final conclusion for this one is, whenever you are considering an NMOS transistor, you should say whether it is on, off, or on. If you want to say that this is off, if you want to say this is off, the VGS value should be less than the threshold voltage of a transistor. That's what you have to keep in your mind. So, or otherwise, if it is not maintaining VGS values less than VTH, it can be either equal to VTH or greater than VTH. So immediately you have to identify that the MOS transistor is set to be in on mode. So when it is in on, there is a two possibilities again, whether that is a linear mode, linear region of operation, or saturation mode of operation. If you want to say that the MOS FET is in linear mode of operation, VDS value is less than VGS minus VTH must be holds good. Otherwise, VDS value is less than or equal to, greater than or equal to VGS minus VTH. So this picture is, it should be there in your mind. Which transistor is on, which transistor is on. If you want to say that the transistor is on, what kind of transistor, what is the equation that holds good, all these things. So in the next class, what we see, so when the transistor is off, what kind of current equation? When transistor is on, what kind of current equation should be there? We will see in the second unit. Okay. So far we have to consider only the qualitative analysis of the MOS transistor operation. Okay. We stop here today. We will see the remaining things in the next class. Thank you. I will, sir.